Okay, so Lagrange error bound is going to be similar to the alternating series error that we saw, but what it does is it allows us to determine how close an approximation is using a finite number of terms to an actual value that we don't know the value of, but it doesn't give us the exact error, but it gives us a bound. So again, we know that we're going to be within a certain level of accuracy of the actual answer. And this works for all polynomial approximations. The alternating series error that we saw yesterday works only for alternating series, okay? So this was advanced by Joseph Louis Lagrange. It's sometimes called Lagrange error bound, Lagrange error. It's sometimes even called Taylor's theorem remainder. It's all kind of related. It'll usually be asked for you to find the Lagrange error bound, okay? Unless it just specifically says, like yesterday, find the error of an alternating series. All right, so suppose you didn't have a calculator, hypothetically, but we were interested in the value of sine of 1. How could we approximate the value of sine of 1? Methods that we've learned, or maybe other methods. How can we do it? Yeah, we could do a linear. We could do a linear approximation. That would be first degree. Let's see if I have that tangent line approximation. Right, that could be one of them. Where would you center it? If you wanted to figure out sine of 1, where would you center your approximation? Yeah, 0 would be a real good one, right? Because 0 is close to 1, and we know the exact value of sine of 0. So a tangent line approximation. What else could we do? Hello, Janie. Oh, thank you. Well, we could use the idea that lines are easy, and we could then split it up and use Euler's method, break up tangent line steps into multiple steps, which keeps us hugging the curve a little bit closer. So that's another one. This one's an easy one. We could eyeball it on the graph, right? We got the graph of Sahala. Looks like this. This would be pi halves, which is about 1.57. So 1 would be somewhere right around in here. And we know it goes up to 1 and starts at 0. So that would be a real crude way, right? Eyeball it. It's 1/2-ish, right? 1/2-ish. That's the eyeball method. You can compare it to like sine of pi thirds, which is square root of 3/2. It's like 0.8 something. Pi thirds is a little bit bigger than 1. So square root of 3/2 should be a little bit bigger than the answer. So there's lots of different ways we could do it. Or, of course, as we mentioned in 9.2, we could use a Taylor polynomial with a degree bigger than 1, because that's just a tangent line approximation. And remember then, the more terms that we add, the better the approximation, and the further we can venture out from the center to get further and further approximations. But the trade-off is we're now evaluating a polynomial of higher degree, okay? So what we want to work on then is, okay, if I use a Taylor polynomial of some degree, I want to know then how close that is to the actual. In other words, what remains. And that's going to be what's called the error. All right, so here we go. If a function exists, we could say that it's equal to your polynomial approximation plus the actual remainder, right? Okay, so this would be like the actual is equal to the approximation plus the remainder we sometimes call the error, right? They're interchangeable. But we're not going to be able to know what the error is. So if we simply solve that, we get the remainder is equal to the function minus the polynomial, and this would be then the actual minus the approximation, and we can call that the remainder. And what we typically do, remember, is we take the absolute value of it. If you don't take the absolute value of it, then it could be informative, because then the sign will tell you if your approximation is too big or too small. And remember, with alternating series, that's always a possibility. All right, so when we write it mathematically, we say then the true function value at A is the polynomial approximation using an nth degree polynomial, that's what T sub n is, plus the remainder, which is R sub n. So that's what we call this. This is the remainder using an nth degree polynomial. So we're back to polynomials now instead of series. All right, and so again, you could solve that for the remainder. It's the actual function value minus the polynomial value. And again, if you want to throw absolute values around it, we can just look at the magnitude. All right? So that's what it's going to look like. It's going to look like that. But here's how we can find it. All right? The remainder then, using an nth degree polynomial at some value of a, is of course equal to, again, the approximation minus the actual. But here's where Taylor's theorem comes in. It's going to be equal to the n plus first derivative at some x value, call it z, over n plus 1 factorial times, instead of x minus c, it's going to be a minus c, right? Because this is at x equals a. This is the specific value we're trying to approximate it, minus the center to the n plus 1. So notice this has the look of Taylor's coefficients, right? To generate Taylor's terms, we have in general, the nth derivative at the center, all over n factorial. These were the coefficients. And then times x minus the center to the nth power. Okay, these were the variables. So it has the very similar feel to it. The only difference is it's the n plus first derivative, okay, instead of the nth derivative. And instead of just having x minus c, we're going to be plugging in a specific value of x. Like we did yesterday, we plugged in, what was it, arctangent of 3/4. We let x equal 3/4, okay? But it all comes down to this right here. What is z? We're not going to know what z is, okay? If we knew what z was, we'd be able to figure out what the actual value is. So here's what we're going to do. We can actually come up with a upper bound on this. We want to find an upper bound on the nth plus first derivative on the interval from a to c. Okay, I should say on the closed interval. That's what we're looking for. Okay, if I don't know what the actual value is of the nth derivative at some special z to get the actual error, I can bound it by finding the upper bound, which is basically going to be the maximum. Okay? We're trying to find the maximum, I'm trying to spell that right, trying to find the maximum of the n plus first derivative on the interval between what? On the interval between our center, c, and the x value that we're trying to approximate it at. And it doesn't even have to be in this order. It could also be like this, okay? The value of x that we're approximating at could be to the left or to the right of the center. All right? So what this comes down now to is finding the absolute maximum, which is kind of optimization. But we're trying to maximize the n plus first derivative on the interval between the center and the value of x we're approximating at. If we do that, then we can come up with what's called the Lagrange error bound. All right, so I'm going to skip all that. If you want to read about Joseph Louis Lagrange, here he is in his ZZ Top costume, right? Because there's a song. If this guy got a tattoo, it would probably be that, right? Because if you remember, Lagrange appeared earlier in the year. He was the guy that took Rolle's theorem and said, thank you, Rolle's. We're going to get rid of the requirement that the endpoints have to be the same. And he came up with the mean value theorem and proved it, okay? So he's a pretty influential mathematician. He's not on my wall, but once I make room for Euler, maybe I'll put Lagrange up there, all right? Let's try it out, okay? Let's try it out. This one's going to be calculator permitted. The best way to learn how to do this is just by doing it. So if you want to grab a calculator, I'll let you grab a calculator. There's my calculator. Let f be the function with 5 derivatives, okay, on the interval from 2 to 3. Let f be a function with 5 derivatives on the interval from 2 to 3. Assume that this is true. Assume that that is true for all x in the interval from 2 to 3. Now, what does that mean? This gives us then, this is an upper bound or a maximum for the 5th derivative. This is going to be one that just lets us get our toe wet. That's the maximum value or an upper bound for the fifth derivative everywhere on the interval between 2 and 3. If we then let a fourth degree Taylor polynomial, t sub 4 of x, for the function f centered at 2, if we use that polynomial to approximate or estimate f of 3, what types of questions are we going to be asked, okay? It says, how accurate is the approximation? Give 4 decimal places, okay? So here's the idea right here. We want to know what f of 3 is, but we don't know what it is, okay? So we could say then that f of 3 is approximated, as they told us, by a Taylor polynomial of 4th degree at 3. Yeah? Okay? And so then the question is that a good approximation or is it a bad approximation? Well, we don't really know. If we knew what the actual error was, we can find the actual value. But what Taylor's theorem or Lagrange error bound does is allow us to find an upper bound, just like with the integral error and the alternating series error. So here's what we could say. We could say that the error, which is equal to, we're going to call that r sub 4 of 3. Okay, so that's kind of the notation we use. R for remainder. The subscript refers to the 4th degree polynomial that gave us the approximation, and then we're evaluating it at 3. It's going to equal the absolute value of f of 3. Well, let's do it the other way around. Let's do t sub 4 of 3 minus f of 3. Or you could flip that around. We're taking the absolute value of it, right? That's the actual error. Okay? What we want to do is figure out then what the upper bound is for that. Okay? So now, how can we do that? Well, Taylor's theorem says that, in general, if you are using n terms for an approximation, the remainder of using that many terms is going to be equal to this. Okay, and that's where the n plus 1 comes in. So for us, since we use a 4th degree polynomial where n was equal to 4, the error is going to be the fifth derivative at z. All right, let's come down and write that. This is going to be equal to the absolute value of the fifth derivative at some magical mysterious z, all over 5 factorial times x minus c to the fifth. Okay, now our center's at what? 2? And we're evaluating it at 3, all right? So this is our x value. That's our x value. Okay, so 2 is the center. So again, it has the same feel that the Taylor terms have. The only difference is we're plugging in a specific value of x for x. Now here's the deal. We don't know what that is. We don't know what the magical x value is on the interval between 2 and 3 that's going to give us the exact value to get the exact value of the error. But what do we know about this right here? If the fifth derivative's magnitude is at a most 0.3, then we can use that as an upper bound for that numerator, which means then we can say that this is less than, we can substitute it in essentially, 0.3 over 5 factorial times, and what's 3 minus 2? 1, all right, so we can simplify. So again, that's not going to be the actual error, but because the fifth derivative is no bigger than 0.3 on the interval, using that as a safe upper bound is good. Now, Colin, among others, might ask, can't we just use an arbitrary upper bound like 7, right, and be safe, right? You asked that one time, can't we just go out further to be safe? And the answer is yeah. But if you start going out too far, you're kind of ruining the whole idea of trying to figure out how accurate it is, right? So what we're trying to do is we're trying to find the smallest safe upper bound by which we then know for sure the error is going to be somewhere less than that. If you go too big, it ruins it, right? You can always say, if I add up the first 4 terms, I'm pretty sure that approximation is going to be within 22 gazillion of the actual number. That kind of, it's purposeless, right? So what we're doing here is we're finding the maximum value on an interval, the safest upper bound that we can come up with, all right? And now all we got to do is evaluate that. So let's go ahead and use the calculator now, because 0.3 over 5 factorial is kind of gross. 0.3 divided by 5 factorial, which remember for y'all is math probability 4. And that's equal to 0.0025. Right? And I'll write that down. So that's the deal right there. I don't know what the actual approximation is when I use a 4th degree polynomial, but I do know that that sum is going to be, bless you, within, what is that, 10, 100,000, 25 10,000ths of the actual number. Okay? All right? So far, so good? This one is easy because they're handing us the number that we needed. They're giving us the inequality. Finding this number is what this section is all about. Okay? All right, so now, part B, suppose that the 4th degree polynomial at 3 came out to be 1.763. So that means that f of 3 is approximately t sub 4 of 3, which is equal to 1.763. Here's the type of question you might be asked then. Use your answer from A to find an interval in which f of 3 must reside. Use your answer from part A to find an interval in which f of 3 must reside. So here's what we're going to do. Kind of like we did with alternating series. We don't know if the series alternates or not. So what we're going to do then to get the interval, f of 3 then is going to have to live somewhere between, okay, and we'll put brackets here to include them, the polynomial approximation minus the number we found up here, 0.0025. That gives us a safe lower bound. And then the 4th degree polynomial approximation at 3 plus the upper bound on the error. So kind of like we did also with the interval the alternating series test. With the integral test, we didn't need to subtract anything because remember, dogs, cats in prison, your terms were positive. But in general, for a polynomial, it could be an alternating. So let's go ahead and see what that actually is then. We can say f of 3 is going to fall between, and using brackets is fine. So let's go ahead and do that. I'm going to store this as alpha A, so I don't have to type it. And then we take our number of 1.763, and we subtract the error bound to get a low point, 1.7605. And then we just add it to get the upper bound of our interval. Kind of has a margin of error feel from statistics. 1.7655. The only difference is margin of errors have confidence intervals. We are 100% confident now. That's the deal. We are 100% confident that whatever the actual value is for f of 3, it's going to fall between those two numbers. Okay? So, could we put parentheses around there instead of brackets? Well, in this case, yeah, because that's strictly less than, those could be open intervals. So if you want to do that, you can. You're not going to lose anything by just adding the endpoints there. So now that you have the interval, you're going to get some follow-up questions then. Could the actual value of f equal 1.768? Why or why not? No, okay, no, comma, since what? Yeah, it's outside the upper bound there, right? Is it in the interval? That's the easiest way to answer it. Is it in the interval that we created? No. Since 1.768 is not, I'll just answer it that way, not in the interval, I'm going to go ahead and say from part B. So this could be a free response question, and that's how you would answer it. All right? Part D, could the function value be 1.761? Yes, it very well could be. Yes, and then of course the answer would be since 1.761 is in the interval from part B. All right, so this again was an example that we could do to get our toe wet, just kind of test the waters. The idea is what you want to understand at this point, right? Taylor's theorem, or Lagrange error bound, gives us a way to find a maximum value for the error, a safe maximum value that's authentic. It's not outrageously big. It's actually the smallest upper bound that we can use, so that we're 100% accurate. The actual sum falls within that range, okay, of our approximation. All right, comments, questions so far? If you want to see a derivation of this formula, I know Khan does a real good job. He actually derives Lagrange error bound, or Taylor's remainder theorem, as it's sometimes called, which is pretty neat. It's like a 8-minute video. It might be worth a good watch if you're curious. Okay, we're not going to get into that here. We just want to know how to use it. So again, Z is the magical value that gives us the true error. We're not going to be ever interested in finding that number. What we're going to be interested in is finding the maximum value. We want to find the maximum value, a safe maximum value of the n plus first derivative. Now remember, that's kind of like the alternating series error. That's the first unused derivative term, right? So it's basically Taylor's rule, and you're going to take the first unused term and maximize that derivative, and that'll give you an upper bound. All right? So let's try it on example 2. Calculator per minute again. Let's return to our original quandary, approximating sine of 1 with an idea of how to approximate using Taylor's theorem. So now it says to find the 5th degree Maclaurin what? Series or polynomial? Polynomial for sine of x, and then use it. All right, so let's go ahead and do that. So now we're going to say sine of x is what? Equals or squiggles? Squiggles, approximately, right? The difference between series and polynomial. If you want to give it a name, I'm going to call it m sub 5 of x. M for Maclaurin, 5 is the 5th degree. So remember, if you're generating a polynomial, they'll tell you what degree to generate. If you're generating a series, they'll tell you how many terms to generate. We're in here till 11:55. Okay. So being sine, we've memorized that we can put an equal sign there. Sine is odd, so it starts with what? 1 or x? Yeah, it starts with x, right? So it's x, and then it alternates minus x cubed over 3 factorial plus x to the 5th over 5 factorial. Plus dot, dot, dot? No, stop right there. All right, so there's your 5th degree Maclaurin polynomial for sine. Now it says to use it to approximate sine of 1. All right, so here we go. Sine of 1 is then approximated by m sub 5 of 1, which is equal to 1 minus 1 over 3 factorial plus 1 over 5 factorial. So I know that's an exact answer, but I'll go to the calculator now and type that in. And because it's only 3 terms, I think I'll just type it in instead of kind of generating it with sigma. 1 minus 1 divided by 3 factorial, math, probability 4, plus 1 over 5 factorial. All right, so write that down. I'm going to store that as alpha A, because we might have to come back and use that. So 0.841, and then I'm going to put equals A. All right, so yeah, when we eyeballed it, it's about 0.5, right? It's half-ish. It's a little bit less than the square root of 3 halves. Okay, cool. And now it says, use Taylor's theorem to find the maximum error for your approximation. So again, you're going to have to recognize how they're asking this in a couple of different ways. Taylor's theorem, maximum error, that's the same thing as Lagrange error bound. All right? So here's what we're going to do. Notice in this case, n was equal to 5, right? So what we're going to do here, we're going to go ahead and say that the error, we're going to write it a lot of different ways. The error is actually equal to r sub 5 of 1, which is actually equal to, here's another way that it could be written, sine of 1 minus m sub 5 of 1, right? That's another way to write it. It's the difference of the actual and the approximation. And those could be flipped either way, okay? So those all mean the exact same thing. And they could ask you in any of those formats. We know that that's equal to the absolute value then by Taylor's rule. Since we used n equals 5, what's the number after 5, the integer? 6. So it's going to be the sixth derivative at some magical z value over 6 factorial times x minus c to the 6th power. Well, what's our center for Maclaurin? 0. And what x value are we evaluating it at? 1, okay? So that's the difference. Instead of x minus 0, we're plugging in the actual x value. We're evaluating it, which is 1. Not necessarily. You could go straight to the next thing, which is the inequality. I would recommend showing that, though. I would recommend showing that because it's going to help get you set up. So here's the thing. I can put less than now after that if I can find the maximum value of the 6th derivative, the absolute value of it. All right, so here's what it comes down to. I want to find the maximum value of the absolute value of the 6th derivative of sine of x on the interval between the center and the value of x we're approximating at. Our center is at 0, and we're approximating at 1, right? So in this case, that's the center, and this is the x value that we're approximating it at. If you can remember that, that's the whole thing behind Lagrange error bound. That's what we need to find. Okay, so let's try to think about it without a calculator. Sine of x, of course, is Sahala, and it looks something like that. So here's 0. 1 is going to be right around here somewhere, yeah? Now, here's what's kind of funny. If I'm trying to find the maximum value of the 6th derivative, what's the 6th derivative of sine? It could be something, right? But I'm looking for the absolute value. So the derivative of sine is cosine, the derivative of cosine is negative sine. When I get to the 6th derivative, it's either going to be a sine or a cosine, yeah? And you can actually figure it out. You want to? It might be fun. F is sine, F prime is cosine, or you can use modular, right? You know it repeats every 4, so you could do that as well. That's negative sine. The 3rd derivative is negative cosine. The 4th derivative is back to regular sine. So again, there's the modular part of it. The 5th derivative is cosine. And so now the 6th derivative is negative sine. Now, because we're trying to maximize the absolute value of it, that's just sine, right? So we can actually graph sine. Now, here's the deal. On the interval from 0, the center, to the value we're trying to approximate it, the maximum value, the absolute maximum value, is at the right endpoint, isn't it? So the maximum value of the 6th derivative is the value at the right endpoint, which would be sine of 1. Does anyone see a problem here? I'm doing this whole process so that I can approximate sine of 1, right? The maximum error is going to be that same value that I'm trying to approximate it. So we can't really find that value, right? It kind of defeats the purpose. We're defining the word dog with dog. It doesn't work. So here's the thing, and this is what you allow yourself to do. What then would be a number? I don't want to come up with a number smaller than that. I don't want to come in smaller because then I'm not necessarily in the safe window. So if it's not an exact number that you can figure out, you want to go to the next biggest number that is as close to that as possible for which you actually know the value. What would that be? Pi thirds wouldn't be bad. That's square root of 3 over 2. Right? So you could actually use square root of 3 over 2 as an error. What is square root of 3 over 2 equal to? Without a calculator. Point something. So you could do that. You actually can. What's the nicest number to use? At pi halves, what's the max? 1. Okay? So there you go. If you used y equals 1, notice, and this is where some students kind of like, they don't allow themselves to do this. So you have to understand the whole idea behind this. We don't have calculators. We can't compute transcendental functions very easily. So we step outside of that interval. We don't go inside, right? You don't pick 1/2 because then the error might be bigger than that. So you step outside it and you pick the first value outside that for which you know the value, all right? So basically, for any sine or cosine graph, you can always use 1 as the maximum error, right? Because the amplitude of sine and cosine are 1. So I'm going to use 1 as my upper bound. Now that I've done that, here's what we could do. We could say then that the error is going to be bounded by, it's going to be less than, and I'm going to substitute a 1 in right there. 1 over 6 factorial, and then 1 minus 0 is 1, so that's your answer right there. And that's a typical thing to do for sine and cosine, to use the maximum error of 1. If the amplitude were 2, we could use 2 as a maximum error. If the amplitude were 3, we can use 3 as a maximum error. All right? So let's go ahead and compute what that is. 1 over 6 factorial. That's, again, mass probability 4. And I'm going to store that as alpha b. All right. So now it says part B. Use your answer from A to find an interval that bounds sine of 1. So here we go. You can either write it in this notation, or you could say sine of 1 falls between, and I always like to just use brackets there. Let's go ahead and write it. My approximation was A, so, oops, what did I do? Yeah, I stored it as A also. I'm an idiot. Let's store that as B. Okay. Do as I say, not as I do. Luckily, we can come back up here and grab that again. Restore that as A. There we go. And now my lower bound is going to be alpha A minus alpha B. And by the way, if you stored them as A and B on your paper, or in your calculator, feel free to write them as A and B on your paper. So 840, I'm going to put a couple more decimals here, 27. And then alpha A plus alpha B is 0.84305. All right. So apparently sine of 1 is going to fall somewhere in between those two guys right there. Now, we could probably make that interval a little bit smaller, can't we? If you happen to know, like, the square root of 3 over 2's value, you could use that, and it gives you a smaller window, okay? But for sure we know this is a safe window, right? If we would have chosen smaller, then we don't have a guarantee anymore, okay? So it's a reasonable trade-off is what it is, all right? So now, can sine of 1 equal 0.87? No, right? No. Since 0.87 is what? Yeah, outside or not in the interval, definite article, the interval from B. All right? And that concludes the question. Of course, they could give you another number and maybe it falls. So now, in hindsight, with the computing power of our calculator, let's go ahead. I'll make sure I'm in radian mode. Let's go ahead and figure out what sine of 1 is. Accurate to as many decimal places as it's going to show. It's 0.8414. Does 0.8414 fall in our interval? It does. Okay? It does. So there you go. Lagrange error bound works not just for alternating series. It works for any polynomial approximation. And again, if you use n, whatever, for your approximation, you can find a boundary for the n plus first derivative over n factorial, n plus 1 factorial, x minus c to the n plus first power, right? All right, so far so good? Questions on that? So we've gone really from being handed the number we need to kind of inferring what a safe value would be for like sine or cosine. It comes down to how else can we do it? Well, let's look at another example. Example 3, now no calculator. Write a 4th degree Mach polynomial for e to the x. A 4th degree Mach polynomial for e to the x, and then use it to approximate the square root of e. All right, no problem, we got that. So e to the x, squiggles, it's a Mach polynomial, so I'll use m again, and it's a 4th degree, so the subscript is 4 of x. And now we go ahead and start writing terms until we get to the 4th degree on x. So e is 1 plus x squared over 2 factorial plus x cubed over 3 factorial. There's the first 4 terms. Do we stop there? Nope. because it's a degree, so it's then plus x to the fourth over 4 factorial, and we stop. Okay, and again, we have our squiggles right there. Now I want to approximate the square root of e. So the square root of e is the same thing as e to what power? E to the 1/2 power. So that's going to be approximated by the polynomial evaluated at 1/2. So just like if we were doing like a tangent line approximation. Now I plug it in, and I get 1 plus 1/2 plus, I'm just going to call that 1/2 squared over 2 factorial plus 1/2 cubed over 3 factorial plus 1/2 to the fourth over 4 factorial. Now again, back in the day, these calculations were a little bit tedious, but they were a lot easier than computing powers of e, which is irrational. So it's really a plug and chug problem. If you wanted to simplify that or type it into your calculator, that's fine. But I'm going to leave it like that. That's a numeric answer, okay, on a non-calculator section. That's good. Okay, so I know that's not the actual value because I didn't use infinitely many terms, right? But now it's going to say find the Lagrange error bound for the maximum error when x is less than or equal to 0.5. So that means when we're drifting within 0.5 units of the center, okay? Well, we drifted all the way to the maximum value, all the way out to 1/2. So that's the same thing as just finding the maximum error at 1/2, okay? So let's go ahead and do that. Let's write it out first in all the different methods. We could say that the error is equal to, since I used a fourth degree, we can call the remainder r sub 4 of, and then the x value was 1/2. That's the same thing as saying it's the absolute value of the square root of e minus m sub 4 of 1/2. That's another way to say it, right? So all three of those, again, mean the same thing. And now that is equal to the absolute value of, this is going into the remainder theorem now. If we used n equals 4, the next number is 5. So it would be the fifth derivative at some magical value z over 5 factorial times x minus c to the fifth. So here's where you want to plug in. Our x value is 1/2, and our center is 0. At that point, it doesn't matter if this is x minus c or c minus x, because you're taking the absolute value of it, okay? So you can always do the x value minus the c. So sometimes the x value is to the left of the center. All right, so now it comes down to this. If I can find the maximum value, I want to find the maximum value of the fifth derivative of e to the x on the interval between the center and the value of x, which are these two numbers right here. So on the interval from 0 to 1/2. Well, again, without a calculator, let's look at it. We know the graph of e to the x looks like this guy here. There's y equals e to the x. Here is 0. Here is 1/2. So again, notice on that closed interval, it's continuous. The right endpoint, again, is the maximum value. So we kind of run into the same problem. The maximum error is going to be bounded by e to the 1/2, which is the square root of e. Yeah, so what would we want to do? We don't want to get smaller, and we don't want to use e to the 1/2, so what would be the next value past that we're safe? You could use e, right? That would be going all the way out here to 1, and that would be e to the first, which is not bad, because most guys back in the day memorized e to many values, right? But if we're going all the way from 1/2 to 1, just to call it 2.718, is it going to be much, much harder just to then say, instead of 2.718, use what? What's a number that's just a little bit bigger than that, but it's a lot easier to use? 3, right? Keep it simple, right? Keep it simple. So I would use 3 as a safe maximum value for the fifth derivative. The fifth derivative of e to the x, by the way, is e to the x. So I would use 3 here. So now I can go ahead and write my inequality. Move that down here. So then I know that that is going to be, the remainder or the error is going to be less than 3 over 5 factorial times 1/2 to the 5th. All right. And now it says to find an interval in which it can live. Oof. Well, let's see. I'm going to go ahead and call this A. And I'm going to go ahead and call this B. You okay with that? And so now the interval, we know then that the square root of E is going to live within, and I just prefer interval notation, but you can use that notation. It's going to be the approximation minus the error bound, and then the approximation plus the error bound. And again, without a calculator, I am not going to bother typing that in, okay? But you could verify that on your own. So could we have done better than using 3 as an upper bound? Yeah, right? You could have used 2.718. If you have stuff memorized, like if you knew e to the something slightly bigger than 1/2, you could use that. But most people didn't have that memorized. So the idea here is the trade-off. We want it to be as accurate as possible, but we also want to make it easy as well. Using 3 is a lot better than using 4, right? 4 would be like, nah, that's not good. That's impractical. But 3 is not bad. And so that's the part that some people have a hard time with. And so on the AP exam, how are they going to make sure that everybody uses the same number? Because some people might use, E instead of 3. Well, they design the questions so that everyone's using the same number. They're either going to give it to you like that or in some other fashion, like here, all right? Example 4, back to calculator permitted. The function f has derivatives of all orders. Assume that this, and this are those numbers. So they're giving you the function, the derivative, the second derivative, and the third derivative at 2. Write a third-degree Taylor polynomial for some function f, we don't know what it is, at 2. And then use it to approximate f of 2.3, give 3 decimal places. All right, no problem. So we're going to generate this one from scratch. F of x is going to be approximated by, it's a Taylor polynomial centered at 2, so we should probably call it t for Taylor. And it said a third-degree polynomial, so a subscript of 3. So let's just write it in terms of x first. All right, so we have enough information, really. First thing we do is we write the equation of the tangent line. That would be the y value of 6 plus the slope of 4 times x minus the x value of 2, right? That would be a Taylor, first-degree Taylor polynomial. That would be the tangent line. And now we pick it up with the next one. It would be minus 7 over what? 2 factorial times x minus 2 squared. And let's see, that's the squared, so I go one more. Oh, they gave it to me. Good. Plus 8 over 3 factorial times x minus 2 cubed. And again, I stopped there, no squiggles, because the polynomial, approximation, and I already have the squiggles there. All right, so that should be easy, right? So good so far? All right, now we just plug in. We plug in. So approximate f of 2.3. So f of 2.3, squiggles, t sub 3 of 2.3, which equals, and now you get 6 plus, if you want, 2.3 minus 2 is 0.3. So that just makes it a little bit less writing. Minus 7 over 2 factorial times 0.3 squared plus 8 over 3 factorial times 0.3 cubed. Right? It's a calculator question, so it said give 3 decimals. Because we're short on time, I'm just going to say that equals A. All right? Some number, 3 decimals. Type it in. All right, now, here's where it gets kind of fun. The fourth derivative of the function f satisfies this inequality. Hey, 9 is the maximum value of the fourth derivative for all x in the closed interval between 2 and 2.3. The center and the value we're interested in. Use Lagrange error bound to find a boundary on or an interval in which it can live. So here's again what we're going to say. I'll just say r, instead of writing all of it out, the different versions, I'll just say r sub 3 of 2.3. That is using a third-degree Taylor polynomial is equal to, the number after 3 is 4. So it's going to be the fourth derivative at z over 4 factorial times x minus the center, which is going to be 2.3 minus 2 to the fourth power. All right, and now, what am I going to replace that with? 9, and that's where the inequality comes in. They said less than or equal to there, so you can actually put less than or equal to there, and you're going to get 9 over 4 factorial times 0.3 to the fourth. And there it is. You calculate that in your handheld calculating device. I'm not going to do it. B. Stored as B. And now the interval, f of 2.3, again, that's going to be just the same thing. A minus B, the approximation minus the error bound for the lower bound, and then A plus B for the upper bound. And you would write all that out. All right, and then I'm not going to answer this because we're short on time, but based on the information, could the function value be 6.992? Explain why or why not. What would you simply do? Yes or no. You would compare it to that interval and say yes because it's in the interval from part B, or no because it's not in the interval from part B. That right there is a sample free response question. All right. So we didn't finish. I have one more to go. Example 5. This was from 2011. They, instead of giving people the inequality, they gave them a graph. Okay, so we'll look at that tomorrow. So tomorrow we'll do this, answer any questions you have. 9.4 is due, worksheet, and maybe we'll just work a couple of free response questions over Lagrange error bound, all right? So one little lesson left to go.